Welcome to the second part of PHA 205, which is biostatistics. In part two, we're going to start talking about inferential statistics. In part one, it was about descriptive statistics. Here, we're going to start addressing inferential statistics, and we're starting with an introduction to testing hypotheses. To introduce testing hypotheses, I'm going to make you think of a scenario. And basically, in that scenario, let's say you had a gambler, okay, and that gambler um, is proposing that you play a game. In that game, he's going to throw a dice, and if upon throwing the dice, if he gets a six, then he wins, okay. And let's say that for just purpose of illustration, you'd have to pay him $2. But however, if he doesn't get a six, so if he gets anything but a six, then he loses and you win. And then he will have to pay you, well, let's say, make it interesting, $10. Okay? And so you think that this is interesting and you decide to play. And upon playing, we're going to also think about two scenarios. Let's say um, you decide to play, and under scenario one, so this is scenario one, you play one time and he gets a six. So basically, he won and you lost. And let's say you only had $2 in your pocket, so you paid, and that was it. You couldn't do anything else. So usually in a classroom, I'll ask students, what do you think about what happened here? And students say, well, yeah, the gambler won. Um, yeah, nothing really. But under scenario two, I tell them, well, let's suppose that you actually happen to have um, more than $2 and you decided to play more than one time. So let's say, suppose you were able to play 5 times and the gambler threw the dice and he threw it and he got a six the first time, he got a six the second time, he got a six the third time, he got a six the fourth time, and he got a six the fifth time. And here again, in a classroom, I ask the students, what do you think about that? Typically, the feedback I'm going to get from students when they're going to see something like this is they're going to object. So some of them are going to say that the gambler is cheating. Some of them are going to say the dice is trick. Some of them are going to say, well, all the sides of the dice are sixes and versions of that. And typically the idea is none of them is satisfied with the outcome. None of them is saying, oh, wow, he's very lucky to get 5 sixes in a row. The majority are going to doubt the results and they're actually going to say, no, no, wait, 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 something is happening here. Whereas in the first scenario, rarely somebody is going to object to the situation. And typically, this is like a summation of what testing hypothesis happened. You kind of like ran a testing hypothesis without even thinking about it. So let's try to think about what happened and why you reached the following conclusion the first time and the other conclusion the second time. Let's think about it. What happened? Why, when you played one time and you got a six, you didn't object? You just it ended here because probably you thought in your mind or you calculated what's the probability of throwing a dice and getting a six, and you quickly calculated that to be 1/6, which is about 16.7%. And in fact, getting a six is as likely as getting anything but a six. Okay? So you ask yourself, okay, so getting a six is 1/6, and it happens, right? You know it happens, and you had no reason to object. But let's back one step behind before we started up. Now, to be able to calculate that probability, you actually made an assumption about that dice right there. you made an assumption that this dice is fair, meaning that it's not tricked, it's just a regular. Okay, so we were saying that to be able to calculate this probability right there, you made an assumption that the dice is fair. And based on the observation you observed, you calculated this probability that led you to believe or led you to not have any objection. Whereas under the second scenario, what happened is using the same assumption that you made that the dice is fair, you said, well, the probability of observing 5 sixes is actually 1 over 6, and that is raised to the power 5, and that turned out to be very, very small. How small, actually? Let me figure out how small. I'm just trying to figure out how small it is. That's about 1 per 10,000. Okay, so it's 0, 0, 0, and then the 1. Okay, so this is highly unlikely to occur. And therefore, what happened in your mind, you made the rational decision of saying, wait. This thing that I just observed right there, this should not happen. Actually, according to my calculation, it should happen only 1 per 10,000 times. And hence, I was not expecting to see anything like this. However, since it did happen, then I am faced with the conclusion that the assumption that I made at the beginning, where the dice is fair, that has to be wrong. Because if the dice was fair, I was not supposed to see something like this, because that is very, very, very rare to occur. And since it did occur, then I'm better off going back to my assumption right at the beginning and rejecting that assumption and saying, no, the dice is not fair, something else is happening. And so therefore, this is in a nutshell what testing hypothesis is all about, where actually we applied the same rationale, the same thinking in research, in medical research, or actually in any kind of research. So let me try to do a recap here, okay? So basically what happened is that you had a certain setup, okay, playing against a gambler. You made an assumption about the dice, and that assumption was that the dice is fair. Okay, so you said to yourself the dice is fair, and then, and then you run an experiment or you run a series of observation, and based on the observation, you were able to calculate a probability. Now that probability is calculated based on the assumption that you made right here. And here, two things can happen. Either you're going to get a very small probability, meaning that whatever occurred is not supposed to occur. This is the second scenario when the gambler got a lot of sixes. In that scenario, you say to yourself, well, this should not have occurred. And since it did occur, I'm going to go back to my first step, which was my assumption, and I'm going to just refute it. I'm going to reject it. The other thing that can happen is that you could get a probability that is not small. I mean, I'm calling it big, but it doesn't have to be big. It's just not small. In that condition, you say to yourself, okay, well, what I'm observing is likely to happen. There's nothing funny about it. And therefore, I just have to accept whatever the observation is saying, meaning that whatever the assumption I made up here, I'm just going to hold it and accept it. In research terms, we call this the failing to reject the hypothesis. Now, so far I haven't actually addressed the hypothesis, but I'm going to just do that in a second, okay? So let me outline the actual step of testing hypothesis and hoping that when I'm going to do that, you're going to see how they relate to the steps we just discussed. Okay, so what are the steps of testing hypothesis? Um, okay, so before we actually start going over the steps, I want to mention one more thing. Um, when we started thinking about the probability, and we decided that either the probability is going to be small, or is it going to be not small? I mean, big, but maybe I should say not small. Here comes the issue of how do we decide if it's small or not small? Obviously, remember that a probability goes from 0 all the way to 1. And somewhere between 0 and 1, you need to draw a cut point below which a probability will be considered small, and above the probability will be considered to be not small. So where do we draw that line? If you remember a minute ago when we were doing the example of the gambler, when the gambler got a 6, that probability calculated was about 16-17%, and we didn't consider it to be small. Obviously, the cut point is not going to be above 17%. It has to be lower than 17%. When I ask students about where they think this cut point should be, usually I get answers like 1%, 1 per thousand. Some students say 10%. The reality is that the medical community or the research community at one point in time decided that they're going to adopt a cut point of 5%. Otherwise 0.05. And this is the cut point below which the probability is going to be considered small or rare, and above which it's going to be considered not small or not rare. Now, this cut point, we refer to it in literature as alpha. We call it alpha. So if you're running an experiment or study or research and you get a probability that's less than 0.05, you consider the outcome to be rare. If it's greater than 0.05, it's considered not to be rare. So let's go back to our steps for testing hypothesis. In the slides a minute ago, if you remember, I started you with the assumption. But in fact, right before the assumption, remember we made the assumption that the dice is fair. And at the end, we either accepted that the dice is fair or rejected the dice is fair. Now, if you're going to reject the dice is fair, you need to get yourself ready to what could it be. So if the dice is not fair, then then you have to have a conjecture. You have to have another idea, and that idea is that the dice is not fair. So actually in research, we start up with defining what we call the null and the alternative hypothesis. So you're going to write two hypotheses. The first hypothesis in our example was the dice is fair, whereas the alternative hypothesis, that is where the dice is not fair. Now, the null hypothesis typically is the hypothesis that declares that there's nothing odd going on, that things are as at their face value, that you're not expecting any change, any difference, therefore the dice is fair. In research, or actually in this class, we're going to write the null hypothesis always as something is equal to something. And so we're going to have an equal sign, all right? The alternative hypothesis has to define everything else than what the null hypothesis defined. So the alternative hypothesis how to account for all other possibilities. So what you're going to do is you're going to take the same, but this time you're going to say it's not equal to whatever that was. Okay? So going back to the example of the dice is fair, you could have written that the probability of getting a 6 is equal 1 over 6. Okay, see how something equals something. And the alternative hypothesis is going to be that the probability of 6 is not equal to 1 over 6 without committing yourself to any specific value. You're just saying, okay, it's not equal to 1 over 6. And you're letting yourself ready to to accept any other possibilities as long as it's not 1 over 6. So that is the null hypothesis and the alternative hypothesis. You get yourself ready for having a null and an alternative hypothesis. Then comes what we were talking about a minute ago, which was actually the assuming, the assumption. Okay, so now that we finished with the null and the alternative hypothesis, we're going to we assume. Okay, remember with the example of the gambler, we assume that the dice is fair. So actually, we're going to assume that the null is true. We're going to say, okay, this is my starting point. My starting point is that the null is true. My starting point is that things are at their face value. My starting point is that there's nothing going on. Okay, there's no change, no difference, nothing. Things are as you expect them to be. Okay. And also part of your second step, right away, right here, you're going to decide on your alpha. Remember your alpha? We said that alpha is the value for which you're going to decide if the probability that later on you're going to calculate, if that probability is considered rare or not rare. The typical value as alpha, as we said, is 0.05. If nothing else is said, you stick to 0.05. But just in case, in some research areas, they might want to have a lower alpha. In other research areas, they might want a larger alpha. So before you do any calculation, you need to decide on your alpha. You need to decide what is your alpha going to be. Otherwise, if you wait on the results and then you decided alpha, it's like flipping a coin, and after seeing what you got, you call it. You know, when when you flip a coin, you call it before you flip it. Okay? So therefore, that was step number 2. Step number 2 is going to be the assumption that we discussed. Okay? So step number 1, you define the null and the alternative. Step number 2, you're going to assume the null hypothesis to be true, and you're going to set alpha. Step number 3, you're going to when we're dealing with the example of the gambler, we jumped to step number 4. We calculated the probability. But many times you'll see that in research, to get to that probability, you need to calculate a test. So it's either you're going to calculate the z-test or the t-test, depending upon the scenario that you have in front of you. So step number 3 is using the sample, using your results, you're going to calculate a test. The tests that you know so far in this course are either the z, where it's x bar minus mu over the standard error of the mean, sigma over root square of n, or the t, which is equal to x bar minus mu. So far it's exactly the same, but this time you divide by the standard deviation of the sample over root square of n, and if you remember, that has the degrees of freedom. Okay, so these are the 2 tests that you know if you're dealing with numerical data. If you're dealing with categorical data, then you would use the z, which is equal to p, which is the sample proportion, minus pi, which is the population proportion, over the standard error of proportion. And if you remember, that was pi into 1 minus pi divided by n. Okay? So these are the 3 tests that you know how to calculate so far, right? So that is step number 3. Step number 3 is just calculating the test. And why do we calculate the test? We just calculate the test so that we can actually get to step number 4. And step number 4 is calculating the probability. Remember, this is the part where we're going to be able to use to decide whether what we observed is rare or not so rare. Now let's define this probability. This probability actually has a name, and that name is p-value. Research, we call it the p-value. What is the p-value? Well, it's the probability, okay, of observing results like you observed in your sample. So observing results that you observed, or as extreme as those results. So now you understand why we actually talked about as extreme as. So observing results as extreme as the results or that you observed in your sample with a condition, so it's a conditional probability. What is that condition? The condition that you made in step number 2, that the null hypothesis is true. Okay? So this is the definition of that probability. Let's see if we apply this definition to the probability we calculated with the gambler. The condition with the gambler was that the dice is fair, and actually we did that. And the question, the probability that we calculated is what's the probability of observing the results that we observed, which was 5 sixes in a row. Or as extreme as. Well, in fact, in the example that I used, we didn't calculate it as extreme as, because that would require to calculate probabilities that would be as extreme as 5 sixes in a row. And that would be 5 fives in a row, 6 fives in a row, 6 fours in a row, 6 3 in a row. But I don't usually talk about that because it confuses students. So for the purpose of the scenario with the gambler, it's fine. But when we start going to use, when we're going to start using actually the actual p-value, and you'll see in the lecture, you're going to understand why we used as extreme as. Okay, so that is the probability that you're going to calculate. It's the probability of observing results that you observed or as extreme as that with the condition that the null is true. Then, once you've done that, you actually now have your probability, which is your p-value, and things are going to get very simpler now. So you're at step number 5. Step number 5, you have your p-value on one side, and you have your alpha on the other side, and you're going to compare your p-value to alpha. Now, why you do that? You do that to figure out if your results were rare or not. So by comparing these results, if your p-value happened to be less than alpha, that means your results are rare, and therefore you're going to say, I did not expect to get a result. Therefore, my starting point, which was my assumption, what was the assumption? That the null is true. Okay, so my assumption that the null is true, that is going to be not acceptable, and therefore I'm going to reject that assumption. And therefore I'm going to reject that the null is true. On the other hand, if your p-value comes out to, p-value again is the probability that you calculated, if that comes out to be greater or equal to alpha, then whatever you observed is not rare, and therefore you come back to your starting point. The starting point was the null is true, and you say, well, I'm going to have accepted. I cannot reject it. And you just stop there and say, okay, that's it. So if you read the steps that I wrote down here, step 4, use the test to calculate the p-value. Okay. Step 5, compare the p-value to alpha to decide if the observed results are rare or not. Then step 6, if the p-value is greater than alpha, meaning that the results are not rare, therefore you cannot reject the starting point, which was the null hypothesis, and you accept the null hypothesis. However, if your p-value came out to be less than alpha, it means that your results were rare, and therefore you'd have to reject the null hypothesis. Here, that's the null hypothesis. And when you reject the null hypothesis, then you're going to accept the alternative hypothesis. And that's where you prepared yourself to have an alternative hypothesis. Okay, now step number 6 is called your statistical conclusion. So a statistical conclusion is either accepting or rejecting the null hypothesis. And you finish up by writing a research conclusion. And the research conclusion is where you're going to put your results or your conclusion in words that everybody can understand. So you don't stop by saying or reject the null hypothesis or accept the null hypothesis. No, you're going to say something that people understand. So like with the gambler, you're going to say something like the dice is not fair. That is a research conclusion. Everybody can understand that. Oh, if you fail to reject, the assumption, you say, well, I have no reason to doubt that the dice is not fair, and therefore I'm just going to have to accept the dice is fair. Okay? So these are the steps of testing hypothesis, explaining the steps using the gambler scenario. Now what you need to do is we need to go to our lecture and see if we can make sense of what we just said using the PowerPoint presentation. Okay.